Indeed, we are very excited to be with you today. We have a lot of cool stuff to tell you about and why machine learning AI would be a game changer for networking. So let me start by, with a quick introduction. We'll talk a bit about the telemetry to start, because any machine learning AI journey starts with telemetry. Then we're going to give you a quick update about Cisco AI Network Analytics that we introduced for the first time last year, but we've got new stuff coming up. As Tom mentioned, it's just one more milestone towards an amazing journey. And this is called Cisco AI Endpoint Analytics. We'll give you some demos as well, because we want to show you that everything is real and we're not talking about a futuristic technology. We're really talking about existing product. All right, so with that, let me start by saying a few words about telemetry. Telemetry is really where everything starts, because we tend to jump, when we talk about machine learning, we tend to jump on the algorithm, but it really starts with telemetry. So what are we talking about? When we look at Cisco AI Network Analytics for wireless, obviously we need to have a lot of telemetry in sources of input data coming from the wireless controller, like the WSA telemetry, and many things related to the network, the systems, and many kind of events related to the wireless controller, the access point, down to the end devices as well. But that's not enough. And the reason why we built up that platform, machine learning AI platform that we launched 1 year ago, is because we wanted to go beyond wireless, and wireless was only the first milestone. So this platform that we're talking about is gathering a lot of telemetry from ICE as well, about location, authentication, device type. We'll talk more about how we can use machine learning to help with device classification, a very key topic, but also net flow. And today we won't have a lot of time to talk about SD-WAN, but we have a lot of really cool innovation down the road coming up very, very soon related to SD-WAN and machine learning. So we take all of this data and input sources, and we push that on a common platform. I'll talk a little bit more about the platform itself in a little bit. One thing that I wanted to show you is also how we look at the quality of a telemetry, because the volume of data is one aspect, but that's not sufficient. So I roll a quick video for you, because as I keep mentioning, the journey always starts with the data, the diversity, and the quality of a telemetry. So what do we mean by quality? Well, when you push so much data points, it's not unusual to miss some data sometimes. And in this case, what you look at here on this video, we see many, many different kind of customers, many type of variables, and you can see in the heat map the proportion of missing data for many reasons. It could be that the telemetry is being dropped, cannot be ingested by the platform, and things like that. So with our platform, what we do, we look at all of these dimensions of a telemetry, and we process the telemetry in order to clean up the data, because some machine learning algorithms, they don't like too much when you've got too much of missing data. I could have shown you as well another video related to diversity, because you cannot expect good outcome from an algorithm it has not been exposed to in terms of data sets. So for example, the first time we used our product in a stadium and no data has been shown in the context of a stadium, the algorithm was not performing really well. And it's only after seeing many, many different types of data, that we started to have absolutely amazing results. Diversity is also very, very, very important. So let me talk now about Cisco AI Network Analytics. So in this case here, what you can see is a platform. So we're gathering this telemetry, as I said before. Then we do some local processing, and we make sure that we anonymize the data, because at Cisco we care a lot about privacy. So we do some anonymization thanks to encryption, and we send only anonymized data. And of course, at Cisco, we don't have a key. The key is owned by the customer. Once the telemetry is pushed in the cloud, this is where we're running multiple machine learning algorithms. We go through multiple layers. We'll build machine learning models. We do root cause analysis, and we raise some anomalies, as you see in the demo with Fede in a few minutes. Then the anomaly are raised, and then the MAC address, for example, the location and other privacy information are being decrypted locally on premise. So what do we want to do? Our objective really was to step away from the past 20 years, and because we know that with network management system, what you do is to detect some anomalies using some naive static rules, which are well known for not scaling really well, not being adaptive, potentially raising some false alarms. And also we know that root causing is really sometimes very, very tricky to do. And with a rule-based system, traditional NMS, it has been known as being a very hard task to do. So we moved to the cognitive analytics. So what we do, we process billions of data records. As you see in the demo, this data is then processed. We compute machine learning models. We raise some anomalies based on your own environment. And then we go through another layer that does root causing. So that's really the point of Cisco AI Network Analytics for wireless. So the goal of that slide is now to show you what I believe is really the core of this product. So what you see in this case is just a time series that looks at the average onboarding time. So if you look at the traditional technique, what we've been doing for years and years was to set a static threshold and raise anomalies when you were exceeding a given value for the onboarding time, right? But the problem is that it really depends. It depends on many, many parameters that are network specific. And in the case of onboarding, that could be the number of clients per radio, it could be the congestion state on DHCP server, AAA authentication servers, and all the things. So what we do here in this case, and usually we use the term of baselining, which personally I don't like too much, because the baseline could be a simple observation of a time of a behavior of a variable. In this case, we build a model. So what basically the machine learning model does is to look at multiple input parameters, such as the number of radios, the number of sequences, the number of onboarding events, number of clients, the proportion of clients with one-attacks, PS key, or open authentication, and other parameters. And then what the model will compute is a band that you see on the screen. And the band will tell you, for a given environment, looking at dozens, if sometimes hundreds of parameters, what should be the normal average onboarding time. And here, that's just an example about onboarding time, but we have dozens of use cases like that. So we compute models for the percentage of failures when you do onboarding, for example, when you do roaming, when you compute throughput, you see an issue with failure during the demo about the throughput, for example. And this is done dynamically and for your environment. And this is what machine learning is about in this case. So we have basically 3 types of outcome and that we want to pursue with that product. The first one are real-time anomaly detection, whatever real-time means, but basically what you see is that we keep sending the telemetry, we use the models, we raise anomalies, we go through a second layer of root causing. Automatically, there's nothing to do. Then we raise the anomalies, you decrypt the anomalies, and then you can look at it, right? So this is, again, what sometimes we call AI-driven baselining, but it's not based on the time. This is based on many parameters. The second bucket relates to trends and insights, because it may be very useful to look at other characteristics of the network that may happen over time, over a long period of time, for example, such as a deviation of a behavior of a given access point. That's one of the examples that will be shown in the demo in a few minutes as well. And this is more like an insight of what you can call a trend sometimes. So it's not related to an anomaly or an issue. It's more like an insight and trend. And the tool will keep providing you new trends and new insight as well. The third bucket is what we usually call comparative analytics. And that was an ask that we had from many of our customers who said, look, how do I compare my network to similar networks? So what we do is that because it's a SaaS-based product, we have access to many networks, and we can start grouping similar networks. And then we can compare and show you where you stand compared to similar networks, and not just by looking at the type of vertical, but many other parameters as well. And then we wanted to extend a little bit this concept so that you can start comparing many attributes of your network across your different sites, because it might be useful to see if on a given site, the average throughput provided to the users is different than in other sites and things like that. So this is done automatically as well. We're also using machine learning to do that so that we can automatically show you how you could compare your different sites. So this is this product, Cisco AI Network Analytics. Today is now going to walk you through a demo so that you can see a little bit how the tool is being used. What I can tell you is that the product has been commercially available since around September 2019, and we see a dramatic improvement of a product in terms of number of users. We see millions of events a week, and that allows us to reach a very high quality for the product, and it has been an amazing success so far. So today, I think that the mic is yours now so that you can show you how the product works.
Hi, everyone, and I'm glad to be here to show you a little bit what the product really looks like. What I'm showing you, I will just take over from the last slide from JP and explaining you the three main use cases, the three main outcomes that we can show with the telemetry we use. First of all, our platform, even though we have a cloud-based platform for the data analysis, the data collection as well as the data consumption from the user all goes through DNA Center. So as you can see here, I'm showing you an example of DNA Center where we have a data set loaded. By the way, one word of caution, this demo is coming from a live system from a customer. You will see that some part of the UI, the names, you will not be able to decrypt them because, again, as JP mentioned, this is a real data, but this belongs to the customer. The key is only available to the customer for decrypting. So we can still see the values, but we don't see the actual, for example, MAC addresses, IP addresses, all the personal information is anonymized for privacy reasons. So first of all, the issues, I will start with the issues. So anomaly detection. Here we integrate with DNA assurance. So when you want to access this type of information that we push you back, you will go through the assurance dashboard where you can see along with all the issues that happen in your system. But you can filter out with this filter AI-driven. You can only focus on the AI-driven issues, so the ones coming from the model-based baselining that JP already explained. In terms of the use cases, as you can see, we have a few, and here what the dashboard will show you once you open it is the list of issues that have happened recently for each of the available use cases. So as you see, we have failure for onboarding failures, onboarding time, throughput, like a global throughput per radio or even per application. And we recently added even additional use cases that go into authentication. So we do a baselining per AAA server or DHCP server for regarding the time and failures that it takes to get an IP address, or even association time and failures. I will start by showing you one example of throughput, which is one of the use cases where probably it's clearer about what's the need for machine learning, because there it's really difficult to set a threshold. So I will just show you what this looks like. So first of all, we highlight in the issue title what type of issue it is. In this case, we're talking about a specific group of applications and where it happened. So this will lead you to a specific building where we can have one or more radios that exhibited a given type of anomaly. And here is where, if you scroll down a little bit, you see the core. Again, the main message for us is to tell you that at that point in time, at that site, we got a drop in throughput for example, social application. So here you can highlight, you see the baseline, what is the expected normal behavior, and we highlight in red whenever we got a significant drop from the expected behavior. We also try to, we explain what the problem is about by using our root causing engine. But we guide you through, let's say, going from the more general to the more specific details of the issue for you to fully understand what happened. So aside from this, now you got the idea about what this issue is about. You can drill down, for example, and see, now that we are looking, by the way, into a specific radio, a specific access point, now we can go and drill down into the specific clients that were connected at that time, so they were impacted by this issue. Here is where you start seeing the encrypted information. Here again, this is only a demo thing, right? Because we are using a real data set without having the customer key. But a real customer will see the actual MAC address, the real username, and if you click on those links, you will be taken into DNA assurance for user 360, client 360, so we can integrate with the workflow with DNA assurance as well. In the same way, as JP mentioned before, we want to guide you through the root cause, because highlighting that an anomaly happened because we were not expecting a throughput so low at that point in time is maybe not enough for you to resolve the problem. So that's where the root cause analysis come into play, where, for example, here you can see, along with, we show you again the baseline and the moments in time when the anomaly was detected, and we also automatically pick one or more KPIs that help you to explain what happened. Now, I want to highlight the fact that as much as the main baseline and the anomaly detection is driven by machine learning models, also the root cause analysis is using machine learning techniques to automatically pick up the KPIs that are related to the problem. You can always add more KPIs for visibility because we have a lot more data to show you, but we want you to focus on what we believe is important. And this is how we select the actual KPIs. In this case, we observed that when there was a drop in throughput for this radio, we saw at the same time a huge increase in packet retries, which might lead to investigation on the client side or on the RF side. So this is what we display to the users. And again, we have other use cases, right? So but the idea is exactly the same across all of them. So the flow is the same, the idea is the same. For example, if I show you what onboarding failure looks like, you will see the granularity might change a little bit, because here we are telling you that there was an onboarding failure increase for a given SSID, again at a given site. But from there on, the flow is exactly the same.
I may want to add as well that, as you guys can see, there are a lot of variations of the normal values, and that shows you as well why using a static threshold is so difficult, because even for a given network, we see that it varies a lot over time depending on the parameters and the some constancies and things like that. And that shows very clearly, just on that one today, we see very clearly that you couldn't have set up a static threshold, because in this case, you could have lowered the value very much and then raise a lot of false alarms, or conversely, miss a lot of issues. And that shows very well why we had to learn effectively. And that's true for many, many parameters. So I showed one, you showed another one about the throughput. This one is about the percentage of failed onboarding sessions in this particular case, but we have many, many like that doing exactly the same thing without any human intervention as well.
Yeah, and to add to this, we have different entities for each of the use cases. For example, here we look into an SSID at a given site, and there will be a specific baseline. But for example, a different SSID at the same site will have a different baseline, or even the same SSID at a different site. So all those combinations will lead to the computing on different baselines. So the expected normal doesn't change just in base of the conditions, but even where you are or where you're connecting to, everything is taken into account as part of the model to create a very specific baseline for the context that we are looking at.
So a quick question on that. How much is the client taken into that baseline, considering that different drivers, different client types will also obviously greatly impact that number?
Well, as part of the wireless LAN controller, on the telemetry that you get from the wireless LAN controller, for some of the clients, we have device classification information. For example, for Apple devices, we know what type of device it is. For other vendors, we don't. So wherever possible, we introduce this information into the mix. So there are several KPIs. For example, I don't know, JP, if you want to comment on this, but there have been results explicitly showing the correlation between the type of client connected to the network with the change in the baseline. For example, we observed in the same customer, there was a clear correlation between the fact of the presence of some type of clients was going along with a higher or long or shorter onboarding time, for example. So this is definitely part of the attributes that we elaborate. But the point is, this information is not available for clients, right? So we introduce this client information based on what is available from the wireless LAN controller telemetry.
Exactly, and there are two ways of having access to that. One is through device classification engine. The other one is via the 802.11 kV extensions. It's not always the case that the driver will provide us additional information about the type of client, but when we can take that into account very easily because it's just another attribute to the model. But it's a great question because, as you said, the decision on whether to move to roam and other things is done by the client by definition, and so the anomalies about the stickiness, the ping pong effect, all those things are very much dependent on the type of client.
Yeah, but I have a question around the system overall. How long does the system have to go to school before you can trust the baseline that it's set typically and ignore basically false positives? I'm sure it's different for every network, but is there an average?
Yeah, it's another good question. What I can tell you is that in practice, what we do is that the first time we connect the network, we don't raise any anomalies for about 7 days. That's what we do by default. We looked at the past as other ways to accelerate and do a form of a warm start, if you will, so that we could quickly identify the type of network and apply a model that was trained to similar network. But that was not worth the effort, because we see that after about 1 week, we start to have some fairly good quality in terms of training. And another thing as well that we have not talked about too much is you might have noticed a thumbs up, thumbs down. Well, this way, sorry, thumbs up, thumbs down, so that you can give a feedback to the system about the relevancy of the anomaly for you. Because we know that there's a little bit of subjectivity. You show the same anomaly to different customers. Some customers may look at it and say, wow, that's a great anomaly. And another user will look at that and say, oh no, for me, it's a false alarm. So because there's no ground truth by definition in this particular case, which is not the case when we try to identify device type, for example, it's more of we can use supervised learning in this case, but in this particular case, we cannot. So that's why we use a sort of reinforcement learning loop, and we can adjust the anomalies dynamically. Okay, cool. Any insight, Fede? Do you have any insight for addition to
absolutely. So beyond issues, right, because networks, we don't see only issues. There is a lot of data and a lot of value that we can take even when it's not about issues. So this was introduced earlier by JP. So what we call insights is fundamentally long-term trending. So what we do, we identify outliers in the network. So when there is some device that over a long period of time starts to behave differently from the other devices. And we want to run this exercise to look into all the data across all your access points, all the KPIs that we have available, and do a lot of work of taking a lot of work out of you, because instead of you looking into all those dimensions, we do that, and we highlight what we believe it's interesting to see when something starts to change in the network behavior. So we do it at two different levels. So one would be at the access point or radio level. In this case, we compare APs, how they behave, or if they start deviating from other access points that are located in the same physical building. Or we even do a comparison site-wide, where when you have multiple buildings, we can tell you if there is one specific building which is starting to behave differently. And we cover this across multiple KPIs that go from the actual throughput, client count, or either RF measurements, RSSI, SNR. We have a bunch of KPIs that we cover there, but the idea is exactly the same. We want to identify for you when there is something changing from the norm. In this case, just to reconnect to your previous question about how long does it take? Of course, in this case, 1 week is not enough, because if you want to do a long term, this will require at least 4 weeks of time, 4 weeks of data before we can start triggering insights. So let me show you an example. What do they look like? So once an insight is generated, what we show here again is, in this example, we are comparing access points within a building. So every circle that you see is in fact a radio, an access point, but to be precise, it is actually a radio. You see, this is the 5 gigahertz radio for this access point. We don't know the name again for the anonymization, but the other bubbles here are other access points. But this is the distribution, so the x-axis tells what was the average client count over that week. So to give you an idea about what the load on that IP was. And as you can see, there are IPs that are typically very lightly loaded, but there are IPs that are heavily loaded. But as this always been the case, well, if you look into what we're telling you, and if you see here, every one of these groups on the horizontal axis, they represent the same set of devices, but over 4 weeks of time. So you see, this is the latest week, then the week before, 2 weeks before, 3 weeks before, covering total 1 month of time. So here, out of all these entities, and what the algorithm does, it will highlight one device, the one that has been moving away from the rest of the access point, so behaving differently fundamentally. And as you can see here, we highlight the trend. So we see this is the same device the week before. This is the same device again the week before. Now, is this an issue? Well, it is not. Here, if you can see, we use a color code to highlight what the devices that had issues and how many of them happen in that week. And as you can see, yes, it is true. The one that we are highlighting suffered one issue 4 weeks ago. But then later on, as the number of clients started simply to grow, there was no issue as highlighted by the anomaly detection algorithm. So fundamentally, we cannot tell that there was a problem there. However, we see that something is changing, and we see that definitely the load is growing on this access point. Now, this is what we call a proactive insight, because this is not an issue yet. But as you can see, if this trend is to follow, it might become a problem. You might need to think into reviewing your density or coverage, your capacity, right, to service more clients in the area this access point is located. So this is fundamentally the idea of the insights.
And of course, it's very common to have thousands of APs, and for each access point, we're monitoring dozens of KPIs. And so what the system does automatically is to look at all these groups, look at all the KPIs, and for each AP, try to learn what is the normal behavior and look at deviation. The reason why we did it is because you may have very subtle deviation, which over time turns out to become an issue. And here in this case, you can even see, by the way, the correlation between the APs for which we raise some anomalies and the ones that are deviating in terms of behavior. Do you want to show us a little bit, Fede, how we can compare the APs, maybe?
Yeah, absolutely. So this is the third pillar, right? The comparative analytics. So here we have at least two tools, the peer comparison, where we compare with external customers. But what I want to show you today, given the time we have, is the site comparison. So what we do with the site comparison is fundamentally doing this. We take 1 week of data, and out of that week, we use clustering techniques to determine for a given KPI, what is the low, what is the medium, what is the high value for your network in that week. Based on this, what we later do is to show you, to allow you to pick from a list, both the KPI you want to run the comparison on, of course, the frequency band, and the building. So you pick up 2 buildings from the list, and you can see them side by side and see how they compare based on the fact that the access points that belong to each building might be part of the low, medium, or high group. In the example I'm showing you today, for example, we are looking into RSSI. So the values for RSSI, we determine that a lower RSSI in your network is below next 75 dBm, medium is around next 61, and high is up to next 51 dBm. So this is, again, those are values that change over time. They adapt. So the definition of low, medium, high not only is not fixed, is not static, it's depending on your network, and it can evolve over time. Based on this, when we show you this, the message here is the fact that you see this first site, the one on the left, it has just less than 10% of access points in the lower SSI bucket, whereas more than half of them, 55%, is actually on the good higher SSI values. on the opposite side, on the right-hand side, you see another building where the situation is quite different, because you see that here, 41%, almost half of those APs are on the low RSSI bucket. So if you do just by comparison, you might conclude that, okay, coverage is okay in this building, whereas in this building you see, especially if you look into Next 76, yeah, there are some APs that typically have clients with low RSSI in there. And you can take this level of comparison again. You can move across days. In this is again the same live network as before. So in this case, we have 2 days of data available here to show, but you can see already that the cluster between the 2 days slightly change. And you can also change the KPIs you want to check. I don't know, if I want to check co-channel interference, well, we're checking 5 gigahertz, so typically it's low. Indeed, a low interference here is up to 1%, which is quite expected in 5 gigahertz. You also see that there are some access points. And by the way, if you mouse over into those APs, because we show you the groups so that you can compare the buildings, but you can always go a little more in detail by checking exactly what radius and how many clients, what model of access points we are talking about, so that you can have different ways to evaluate the performance across different buildings. So this is what we have in terms of comparative analytics.
I have a question around utilization. Where do you see this tool being used? Is it for day-to-day operations? Like, would you have this dashboard up constantly on your network team or in your NOC or something like that? Or is it a tool they would go to if there is a problem? Where does it fit into all the other dashboards and tools that that a department would be running?
This, I would say, fits very well both in the monitoring, because you might just have a way to compare how things go, especially if you receive complaints for a given building. You might know and compare with a different building where you don't receive complaints about or as much. Or, for example, if you want to plan an upgrade, right? If you need to plan an upgrade, looking into what are the locations that need for a refresh quicker, or the ones, again, that are suffering more. And even this would be allowing even to see if you have, or in a different way, if you have 2 buildings that are expecting to be the same, you can still compare if the performance is constantly the same, or if there is some variation in there. So I would say it's a little bit both on the both reactive, in the sense that you can compare and see how things have gone, but should help you also for the planning, right? So for in terms of planning or looking into what parts of your network might require some redesign or some refresh.
Super. So today we want to go to the new stuff now.
Absolutely.
Thank you so much for the demo. So what I want to talk about now is what we're launching this year in 2020. What we are announcing is something called Cisco AI Cisco AI Endpoint Analytics. So what I said was, what we wanted to do last year was to announce the first product of a long series related to wireless. We started the work in 2016. It took us 3 years to build a very scalable platform, launch wireless, and this year we're announcing Cisco AI Endpoint Analytics. Okay, so what is Cisco AI Endpoint Analytics about? First of all, the problem is very simple to explain. We want, when the device joins the network, we want to be able to identify the device type. We have multiple dimensions of that, basically, but to make a long story short, many customers, they enforce a given policy that is based on the device type. So our objective is to reduce the task of having to set up a lot of rules so that we can improve the quality of the device classification exercise. So what you see on that slide is the typical workflow. So as many other vendors do, we've got some rules that are pre-configured, and you can also add your own rules. So when the device comes in, we're using a bunch of probes related to ICE, but other probes as well, such as looking at the DHCP protocol, the OUI, and other things like that. The user agent is another one. And what can happen is that the device can match a given rule, in which case we can identify the device type. And if you have a policy for a given device type, you can apply the policy. Of course, now the problem we're trying to solve is what do we do for all the devices for which there's no rule? And it's not unusual to see from 5% to sometimes 30, 35% of devices not matching any rule. It depends on the environment. But when you look at IT and IoT, there are thousands of device types. So here's what we do now with this new product. It's a way, if you will, to use machine learning to help you generate rule automatically and then improve the device classification and reduce the percentage of unknowns. So what the algorithm does is to look at all of the unknown devices and cluster them together by degree of similarity. So the reason for doing that is because what usually customers do is to look at every single unknown device one by one, look at the MAC address, set up a rule, which is extremely cumbersome. So what we do, we recognize the degree of similarity using some machine learning algorithm. I'll say a few words about this type of algorithm later on. We group them together. We give you some additional context. And Fede will show you a very quick demo in a minute. The context is very important because thanks to the context, it helps you tell us what is the type of device we're talking about. So the second step now is that the system will say, all of these devices are similar. Could you tell me the type of device? This is what we call labeling, sometimes active labeling. And then we will generate a rule automatically. If you're happy with the rule, you can accept the rule and we generate the rule automatically. So it's a way to assist you and group together devices that are indeed similar. We have another functionality that I think is very neat that allows us to go across multiple customers. And if we see a given type of a known device that we see with multiple customers, we can compare the levels that we provide for these device types and give you an update about the type of device and maybe say sometimes, you told us it was a coffee machine of type A, but it turned out that everybody agrees this is a coffee machine of type B, for example. So we have all of these mechanisms. I won't spend time on these slides, but I just wanted to say a few words before we show you a very quick demo. Is sometimes people see, and I know that when we talk about clustering, it seems very simple. So you can use an algorithm like dbScan or whatever, what we call density-based type of algorithm. It's just one type of algorithm that can be used. And you look at the device in a multi-dimensional space. So look at multiple attributes. And at the first sight, you may say, look, it's easy, right? You just group devices that are close to each other. And so use a distance so that you can tell which devices are similar by looking at how close they are in that dimensional space. The problem is the quality of the outcome will be mostly driven by the type of distance. And it took us months and many engineers to really design the type of distance. Once you have a distance, it becomes much more easy to cluster things together. So again, we won't go there unless you ask me for detailed question. I would love to answer, by the way, but I'm not sure we're gonna have the time. But it took us a lot of time to figure out the math and make sure that we have a good way of clustering things together. So in the meantime, Fede will switch over, give you a very quick demo. You see, because we wanted to show you that it is real, and you see the UI is extremely simple. And then I'll try to conclude with what's coming next. Fede, would you have a demo for us?
Absolutely.
And I stop sharing. All right, let's go.
Real quick, because again, there is a lot of complexity in the backend, but the UI, we try to keep the workflow extremely simple. So once again, the interface to this is DNA Center. So in this case, you will find the product under policy. It's not about assurance, it's endpoint analytics. So once you land on the endpoint analytics page, you will get a summary about the number of endpoints that have been discovered in the network using either ICE as a probe source or even as DVC using probes extracted from deep packet inspection on iOS 6C, Catalyst 9K switches. And so here we already have a lot of rich information about the endpoints and of course, a lot of rules that classify those clients. But again, what do we do about the unknowns when a rule is not known? And this is where we come into play with the AI proposals. So here we group together the unknown devices, the one that don't have a rule, into a smaller number of groups. So instead of classifying devices one by one, once you need to go and insert custom rules, we can do the work for you to group them together into a group of similar devices. So once you click there, for example, here we have 10 groups of devices. Some are several hundreds. So if you go through the definition of the rule that we propose to you to classify those devices, you will get rid of a huge number of unknown endpoints in one go. So here, fundamentally, we allow you to navigate and show you the number of clusters of devices that we identified, and we show you not just the number, but even the actual attributes that we found to be similar across devices, what forms actually the group. So for example, if I take this type of IoT device, well, we recognize it's an IoT device, but if you look into the available rules, there is no classification for it. Okay, do they look similar? Well, let's see. And if we go into, if you click on next here, we show you as a next step. So first of all, we tell you what are the endpoints, why do we believe that they are similar, and the following step is to tell you, look, if you apply this rule that we propose you, and by the way, this is fully automatic, so it's generated by the system in a completely automated fashion. We let you review that, and if you accept that, you will get those devices classified. In this case, really, the rule is showed there for you for your info, because what we really need from you is the active labeling piece. So when you move to the next part of the workflow, you can give it a rule name as you would do for a custom rule, except the fact that the rule was automatically generated. And you can insert, for example, a thermostat, and you can say thermostat. You can tell us, right? Because there is no rule, so we are not able to tell you what it is, but we are able to tell you that they are similar, so we can guide you through the classification. So you can define one or more of the keys. If possible, we also suggest some labels based on the crowdsourcing data, so based on classification that other customers did. So once this is done, you can move to the IS. Thermostats. You need to give the rule a name, and then you're allowed to move next to the following step, where you can do a final review of the rules, the endpoints that are part of it. And once you click on profile, basically those endpoints will no longer be classified as unknowns. They will actually have their proper classification that you provided. You can also reject the rule if you believe that the algorithm didn't do a good job, either the grouping or the rule. In this case, you can fill a form where we can ask you, okay, again, similar to the thumb up, thumb down that we mentioned before, you can provide help to do a better job the next time. And also, the last thing is, we can propose your rule today about the endpoint that we found out today. However, there is also a workflow that we can propose over time improved versions of the rules. So there is a workflow for modification. So for example, if there is something better that we learn about those endpoints, we have a better way to classify them. We can propose you new rules to update the previously proposed and accepted ones, so that the classification can be even more relevant and more accurate. That's all I have. I hope it's clear.
Thank you, Fede. And it shows you as well, that that's going to ease a lot your task, because instead of going one by one, you can regroup very quickly. We also monitor when customers reject rules, for example, in our backend, so that we can keep improving the clustering algorithm.
I assume that you use Cisco's internal network for your current, environment, so you can teach the machine, correct?
Yes, absolutely.
Okay. I only asked that because I was wondering if there was going to be a difference between what the lab says, and then what happens when we deploy in customer networks. But it sounds like you're running it in production right now.
Yes, I can tell you actually, we've got about a dozen of early field trials in multiple verticals, so that we see whether the system performs well in healthcare and IT and all those things. It varies as well, because some customers, they have a lot of the manual rules, and so the percentage of unknown when you start is not exactly the same. But we believe a lot in this product.
Do you foresee, considering the growing integration with SDA, SD-WAN, ACI, do you ever foresee a lot of this same technology being applied to the WAN?
Oh, thank you so much for the question. You know why? Because that was exactly my conclusion. So what I wanted to say, is that what I'm most excited about, I can tell you, is not, yes, I love this product, but is the fact that it shows that we are on a journey. And so we started again with wireless. Today we're announcing, the classification. In a few months, we will be announcing some advanced security features using machine learning to detect some different kind of attacks, for example. And we've been working for quite some time on SD-WAN. So we have a lot of innovation in this area of SD-WAN that are coming. And the last one that I wanted to talk about a little bit is in the area of application, because all of the customers we have, they talk about application, how can we improve a network so that we can do more advanced application-aware routing, for example. So there's a lot of innovation coming very, very soon. Absolutely.